Hello, Sarah. Can I just test that we are broadcasting okay? Can you hear my voice? Okay, got a thumbs up.
Yeah.
Okay, thanks for joining online, everyone who's joined via Teams. We will be starting in about 5 minutes, so just giving people a chance to join here in person in the room. Got another 5 minutes, and then we'll make a start. Thanks. Right, okay, it's just turned 4:30, so we will make a start. So, firstly, I'd just like to say a warm welcome to the Cheshire and North Wales section of the PWI to our June presentation, which is being provided by Bryan Wedin and Roy Partington of Greenfix. So Roy's going to give us a bit of an introduction, and then he's going to hand over to Bryan, who I'm informed is over the other side of the pond in the USA. So yeah, so I don't think I've got no sectional notices to announce really. We haven't firmed up the talks for the autumn season yet, so just keep you advised on those via the PWI events calendar. And just the usual housekeeping rules, please. So if you keep your microphones on mute and your cameras off while the presentation's on, that'll help things run smoothly. So without any further ado, I'll hand you over to Roy to introduce Greenfix and their slope and track stabilisation systems.
Thank you. Good afternoon, everybody. Thanks for attending in person, and obviously thank you for those joining online. As Les says, my name's Roy Partington. I work for Greenfix here in the UK. We're a leading supplier of ground stabilisation, earth reinforcement, soil stabilisation, and one of our products is GeoWeb, which is the network rail approved geocell for under track stabilisation. We're based down in Evesham, so in between Worcester and Cheltenham, but we cover the country. Presto Geosystems, Bryan, our chief design engineer, will be conducting the talk on GeoWeb, represents. We've had a partnership together for over 15 years. And we, as I said, the GeoWeb is the only network rail approved system for under track reinforcement. And in fact, I kind of go way back to the 90s with GeoWeb and rail. And in fact, I think the first actual network rail, British Rail, whatever it was called in them days, installation was in the 1980s of using GeoWeb under track. So Bryan represents Presto Geosystems, as I said, and we work very closely together, as you can imagine, with a UK and Ireland distributor for the product. And I'm now going to hand over to Bryan, and he's going to talk to you about the applications for the GeoWeb.
All right, thanks, Roy. Welcome, everybody. Thanks for taking the time. Before I get started, can everybody see my slides? Okay, everything's looking good so far. Roy is looking good. All right, so I'll move on. So basically, geocell really has two main attributes. The first is the cell size. It comes in 3 different sizes. Comes in diameters, I call them nominal diameters, of 21, 26, and 45 centimeters. And it comes in 5 different depths, from 75 millimeters up to 300 millimeters. Depending on the size and the depth, it comes in a very bunch of different section lengths. But the project, the type, and the depth that you'd use for a specific project really has to be based on a project evaluation. So for geocells, or any geosynthetic for that matter, please reach out to the manufacturer to get a project evaluation, which really should include the calculations, specifications, and some drawings. So the ultrasonically welded seam, that's where all the connecting points are here on the geocell. That's really the most important function of a geocell. That it's stronger, the seam strength, the stronger that the geocell is going to be. Our geocell is made out of 100% HDP polyethylene. We don't add any fillers, any type of alloys that can make the weld or the cell walls a little bit stiffer, but gives up in seam strength. So when I'm talking today, it's going to be just on HDP geocells. We've invented the geocell technology back in the late 70s with the Army Corps of Engineers here in the States. We've been producing it since the late 1970s. Roy did mention about the British Rail project that we did, the first one under rail in the UK. I actually do have some slides on that one, Roy. So thanks for mentioning it. Depending on the size and the strength, it comes, basically comes tri-folded on a pallet, ships very efficiently, usually anywhere from 12 to 20 sections on a pallet. Each panel has a area of about 230 square feet, so about 23 square meters. A nominal width of 2.6 meters for all of our panels, and then once again variable section lengths up to anywhere from 8 to 16 meters in length. The second characteristic is how you fill it. There's geocells are very versatile in what we can fill it with. Under rail applications, usually we're going to use basically a ballast rock. Anything less than about 1.5 inches in diameter can be filled. But a lot of rail projects that we do actually in the UK is going to be coarse sand. I'll show you some projects as we some case studies here where our infill was just 100% sand. You can imagine if we can use sand infill, that's with the availability of good aggregates, it's a little bit harder to find them, no matter where we do projects around the world. But sand, usually is locally available, less expensive. When we do slope projects, but hopefully I'll have time to talk about that today a little bit. We can fill it with topsoil, aggregates, or concrete. So it really is a very efficient system. The purpose is really just to stabilize and prevent the movement of unstable soils, whether that's vertically or horizontally. Like I said, today I'm going to be really focusing on load support. But we do a lot of slope protection for rail. We do slopes up to about 70 degrees. You can fill it with topsoil, aggregate, or even concrete. Once again, a lot of channel protection that we do. Also retaining walls. We'll do a lot of abutment walls against track all over the world. So here's how 3D confinement works. Basically what you're trying to do is you have a vertical cyclical load, whether that's a tire or a train wheel on a track. You're basically having a vertical stress that's getting down into the subgrade. What we want to do is convert that vertical load to a horizontal load. Basically you got the active earth pressure inside of the cell pushing out. You got the passive earth pressure in the adjacent cell, which pushes back. So really, you're only needing one or two cells to support that load. What it does, we really spread out that load distribution. I'll show you the next slide. But as this vertical load is turned horizontal, so it's into a more or a horizontal load, it basically engages the hoop stress on the cells, which really does support that load. This is a good slide here because it really shows the amount of stress reduction that we can get. A typical load distribution is going to be a 45-degree angle as the load is dissipated into the subgrade. You can see here the high stresses with the red and the tan and the yellows. When geocell stress reduction really does reduce all of these high stresses. It spreads out that load to 60+ degrees, and we call that the mattress effect. So by the geocell, converting that vertical load to more of a horizontal load, you're really widening that stress chart out. A rule of thumb, if you have a load support application, whether it's rail or roadway, we reduce the stress reaching the subgrade by at least 50%. So it's a pretty significant stress reduction. We do a specific calculation, site specific for all of our projects. So we will provide charts that show you the stress reduction that is given throughout the cross section. So I'd like to go over some recent research that we did on geocells. We've been, I said, producing them and selling them over the last 40+ years. There's been hundreds and hundreds and hundreds of research papers done. We've probably done at least 50 tests on GeoWeb. This was one that was basically under track. We wanted to take advantage of some of the recent FEM models, so the finite element models that we do for high stress. We also wanted to use smart rocks, and I'll show you, these are basic vibration sensors that detect how the ballast moves underneath a cyclical load. We did conduct the research here in the States. Yeehan, if anybody has done any unpaved roads or been to any conferences, Yeehan is a very well-respected technical expert. They created the Druhan unpaved road calculation. So I'm sure a lot of people know of Yi. Ben Lashinsky, he did his PhD thesis on geocells at Oregon State, and Hai Hung from Penn State University actually provided the smart rock and the smart rock sensors. So, sorry, my lip just got locked up here. Sorry about that. There we go. So the study looked at about 300,000 pound loads, so a typical heavy car weight. We did speeds up to 75 miles per hour, 136 pound rail. That's when we used standard wood ties, and we varied the subgrade strength from 0.5 up to about 5%. We did about 20 different cycles of this test to really get a good distribution of stresses and a good way we could graph it. Once again, I mentioned we added these smart rock sensors into the GeoWeb. We wanted to see how the stress affects the movement of the rock, whether that's rotationally or in the XY plane. We put it in the GeoWeb, but also we put it halfway between the top of the cell and the bottom of the tie. So a lot of the Class 1 railroads and even railroads around the world have used geocells, and they understand and they learn how the addition of geocells to a ballast, to support a ballast, really reduces any attrition in the breaking down of the particles. So you don't have to do, it eliminates a lot of maintenance and less tamping. So one of the main studies or points of this study was to determine, what happens when you add a geocell to the ballast. So here you can see how the smart rocks measure it. This one here, so it's measuring the ballast rotation. That was one of the points of adding the smart rocks. Whoops. And then the other one is basically how it moves around. So as each cyclical load is applied, we want to measure, how that ballast particle is moving, whether it's rotating and how it's moving back and forth. So this one shows the angular velocity, which is measured by the rotation, so how that ballast particle actually rotates. Here you can see the control section. This is the most important one, because in the geocell, it is confined, so it really isn't going to move that much. But this is below the tie, so this was a 10-inch ballast, so 5 inches below the tie and 5 inches above the top of the geocell. Here you can see without any geocell confinement, significant amount of rotation, of ballast rotation. But with the geocell, you can see it almost completely 100% eliminates any kind of rotation of that ballast. So you can imagine, eliminating that rotation is going to limit the amount of ballast attrition and any kind of tamping. Here's the second one. We're looking at this is how it moves, basically back and forth, and how it moves once again, in the geocell, pretty stable. Here you go below the tie again, 5 inches below the bottom of the tie and 5 inches above the wall. You can see the control section is significant movement of that ballast particle, but you can see with the stabilized with the geocell, how it basically almost eliminates any type of movement. So it really is a pretty significant study that we did to show how and why geocells really limit the amount of maintenance that's required by really reducing the ballast rotation and movement. So, less attrition, you're going to have less tamping, you're going to have to save costs and delay your maintenance cycles. We also did look at the finite element analysis. It's proved something that we've known for a long time, is that we can really decrease the subgrade pressure, as I mentioned before, by at least 50%. Like I said, we can actually tell you site specifically what your pressure will be on your subgrade. By reducing that pressure, reaching the subgrade, we're also going to control consolidation settlement. And another thing is differential settlement. So if you're putting in a new track, the worst thing that can happen, or any type of installation, is differential settlement. So you're going to have a lot of bumps in the track. By using the Geo, it really does almost eliminate any kind of differential settlement due to the spreading out of that load. It really can control and reduce that kind of settlement. So if anyone's interested, we do have research summaries that were prepared by University of Kansas, Oregon State. So if you're interested in that, I'd be more than happy to provide those for you. So now we're going to talk about some geocell installations on your track. Pretty much anywhere you have track, we can add geocells. The biggest advantage, really is going to be on some of those high stress areas, whether it's straight track, frogs, turnouts, crossings, bridge abutments, things like that. But we can use geocell and we have installed it under anywhere under track all over the world. So we have hundreds and hundreds of case studies and a great website that I'll touch on a little bit later. This is the one that Roy mentioned. This was for British Rail. This was a couple kilometer section. British Rail had issues with this one because it was in some really bad peat bog areas. So this installation was carried out It was basically on the Edinburgh to London line. The area was called the Newham Bog. This is where peat layers reached up to about 5 meters. So some pretty bad soils. But really the primary challenge here was the ground settlement. Caused some really bad soil conditions, a lot of track maintenance. They actually had to reduce the speed from 200 kilometers down to about 70. So that you can imagine that increased reduction in speed led to increased travel times, energy consumption. So British Rail was really had to do something here. The biggest problem here is the downtime. They had to really limit the downtime, and their typical approach of excavating and basically filling in with rock was not an option. So they came to us and gave us a deadline and a time frame to limit those service disruptions. So, here you can see this installation was pretty noteworthy because here, we did this in 2 sections. So the northbound section was completed first. And what they did was expand the sections across, and then they just left the unexpanded sections done, unexpanded, so they can come back. Here you can just see they installed actually 2 layers here of geocells. They were 200 millimeter geocells. Here we installed a drainage geocomposite here to enhance drainage across that section. This one was so old, if you can see, I don't know how good the screen is, but this was actually before we added perforations to the geocell. So this was one of our original invention that didn't have any perforations. We added the perforations a couple of years later to increase drainage, but also to increase frictional interlock of the infill material. Here you can just see a better photo, close up of the geocell and the drainage geocomposite in the concrete sleepers and the rail. Here you can see the geocell was filled with crushed aggregate. Here we really minimized the fines to about 10% to enhance that drainage performance. Rule of thumb, you want to keep if you want drainage or enhanced drainage, you want to keep the fines to 10 or 12% or less. Really provide a lot of drainage. So after we did this improvement, it really did improve the stiffness of the track. Within a couple of weeks of both sides being completed, they were able to restore the speeds from 70 kilometers per hour back up to the target speed of 200 kilometers per hour. So a very efficient installation. Now it's going on almost 30 years. So it's been under the track for a long time. And here you can just see the final track. This is a project we did for Network Rail. This was a project on our northern hub, was called the Bolton Exton line. Parts of the track here were enhanced on the northern hub, located on some really soft ground, slow shear strengths, CBRs, around 1 to 2%. So, as a result of that, the standard track depth that was going to be required was as high as 1 meter. Network Rail realized that was basically too expensive to construct. So they contacted us. We've done a lot of work with them. We worked with their track bed investigation team. They were actually tasked with finding an alternative design solution. So we worked with them, and we developed some numerical modeling and also a design method that's using the way we design track here in accordance in the States with the REMA method. That's how we design tracks here in the States. I use that method for rail designs all over the world. The one thing I'll show you in a little bit, Roy mentioned about the Network Rail design method that was sent out. So on this project, the model that we used, and we did it through some testing, we looked at different geocell layer thicknesses, different geotextiles, compared to their standard track design. So the iteration showed that using a track bed design consisted of a 250 millimeter ballast layer, 150 millimeter deep geocells filled with granular fill and about 50 millimeters of sand, would provide basically the similar performance to a standard design solution from Network Rail, but it saved about 100 millimeters of construction depth. So, it's important to point out that the reduction in the track bed thickness, so about 40%, was accomplished by the use of geocells. So it really did save the amount of material costs and installation costs, but it had a track enhancement by about 22%. So 40% reduction in fill, 22% reduction in cost. Here you can just see a couple of the images of the installation. Here a non-woven geotextile was put down, placed with a 50 millimeter sand layer. Once again, that 150 millimeter deep geocell panels were put down, filled as an aggregate, crushed aggregate on this project. So here's they have been doing routine monitoring of this site since the early 2000s, basically starting in January of 2002. This line opened in 2018. The new one with the geosol on it. You can see here the slide shows that the track quality of that 8th mile of the worst top 35 mean, I guess, from the standard deviation. You can see it significantly increased and reduced the degradation of that track ballast. So you can see here, this was their first method when they came in and did some reconstruction. This was over excavation and filling in. Here in 2002, you can see, how that basically a direct line with the track performance degraded. They did some stiffening of the ballast back in 2010. You can see initially a drop, but then right away it got back. When they put in the geocells in 18, you can see a very, very low maintenance that was required. You can see hardly any degradation over the last 3 to 4 years. So it's been a very successful installation. Here you can just see a comparison between the track quality. This was in 2002, and after the first installation in late 2018, you can see from the table that after the installation 2017, you can see that track quality and the deterioration improved significantly. So, the deterioration rate after renewal in 2002 ranged to about 0.9 millimeters per year over those 10 to 12 years. After we installed the geocell, those values went from 0.9 millimeters per year down to 0.1 millimeters per year. So you can see that significant reduction in that degradation of that ballast. Roy had mentioned this before, based on this project and the research and testing that we did, and some other projects that we did with Network Rail, they were very interested in expanding the use of geocells under track. So I worked with Network Rail, and they used a lot of our research, specifically that research I talked about with the University of Kansas and Oregon State, to develop this geocell standard. It is available on their website, so it's the use of geocells in the track bed for Network Rail. It was reviewed, it was peer reviewed by 6 world people recognized rail professionals all around the world. So it is it's a very good design guide to use. So you can use it to develop geocells, cross-section in your designs. Once again, I would highly recommend reaching out to us, and we can help you provide a little more in-depth evaluation for your track and looking at some different factors that lead to deterioration, and I'll show you towards the end of the slides. So here's another project. This was for the Warrington, up in Warrington. This is about 3 miles. It was just north of the Peterborough rail station. The aim of this project really to increase capacity for passenger trains. This was part of I think it was almost a $1 billion upgrade. So it's called the Warrington Drive, and the separation project was built two new track rail lines under tunnels for its existing line. So it opened a couple of years ago, but it really did remove the constraints for the timetable caused by slower freight trains that were on that route, so that had to cross over the line. So it included about 2 miles of construction of GeoWeb, and the main thing that the engineers were looking for here was to really improve the stiffness of the track, along with improved drainage, but also to reduce that over excavation that was required, due to some poor subgrade strengths that they had. So we did use the Network Rail spec. This was the first time that design manual was used, was for the Warrington project. And like I said, we also did a little further dive with our design method, but this was the first project. And like I said, this one had a lot of poor soils. You can see now a close-up of the geocells, with the perforations I was talking about before. This one, the soils were pretty bad. So we actually used a high-strength woven geotextile. A lot of the rail applications, we're going to have some type of separation layer, whether that's a non-woven separator or geotextile, but a lot of times we're going to use an enhanced woven geotextile. When I say a woven geotextile, I'm not talking about like the slit tapes or slit film wovens you might hear about. Those are do not let any kind of drainage. They're basically like a pool liner. So the enhanced wovens allow water to flow freely, from the subgrade above and from below. So it doesn't allow pore pressure to build up. So if you're ever, I think even in Europe now, I know in the States, Australia, South America, they've eliminated any use of slip tape woven geotextiles underneath tracks because of the poor drainage capabilities here. So just something to be aware of if you're doing any kind of design, you don't want to have some geotextiles. But here you can see, this is what I was talking about with that coarse sand. Aggregates were a little bit more expensive in this area, but they had a ton of coarse sand. So here you can see that we actually use coarse sand to fill the geosalt panels. You know, it's really flexible. Like I said, we can use those low quality sands. We don't need the high friction angles. Aggregates, like say a geogrid or a geotextile, because you know that geocell really does provide the confinement. This contractor was, I got to give him a good hand because he actually was very consistent with how we wanted these panels to be expanded. So we actually went out and bought and built these rebar stretcher frames to make sure that that track was aligned, you know, really straight along that whole couple-mile route. So you can see installation is very fast. So you can see, you know, filling it from a side loader on an adjacent track. You know, it goes very fast, especially, I mean, this was taken right from the site over in Warrington. As you can see, is once they're putting down the spill, you know, typically a dozer with a GPS on it just comes and pushes the web into the cells. Really don't have to compact it. If you are going to roller compact a geocell, you got to make sure that you're not, you can roll it, but don't vibrate it, because vibration, especially if it gets excessive, you can actually pull the panel right out of the cross section. So you want to make sure, usually construction traffic is more than enough compaction for the cell. If you are going to try to compact it, make sure it's just a, you know, basically a roller compaction and not a vibratory. Here's another project we did. This is actually out of South America. I like to show this one because it really does show how flexible this system is. This was a 10-mile extension that we had to repair. It was coming from a coal mine. They were getting a lot of contamination from the fines, so it was fouling the ballast. Subgrade wasn't too bad. It was about a 2 to 3% CVR. But they had some drainage issues, you can imagine, with all the fines clogging that track bed. So on this project, really the interesting one on this is we are actually to use we scraped the ballast layer, and it was contaminated. We actually stockpiled it along the whole site. So this was about 10, like I said, about 10 miles in length. Here you can see it's 2 panels of GeoWeb, so about almost a little over 5 meters in width with an enhanced woven geotextile separator. But like I said, GeoWeb, we can use that coarse sand. Just want to keep the fines to about 15% or less, which we tested a lot of this ballast. So we just stockpiled it and they put it into right back into the geocell. So like I said, this was 150 millimeter GeoWeb depth. So reusing that ballast material, that fouled ballast material, saved them between excavating it out, hauling it out, and bringing back in fresh ballast. Saved over 12,000 cubic meters of material. So you can imagine, you know, the cost savings that was, you know, not to the owner, not only in the infill, but, you know, hauling costs. And another thing that they were sensitive about was carbon emissions. So they really, you know, without having to produce that ballast, haul it, place it, they saved a lot of carbon emissions. So that was really important to the owner too. And here you can see that salvage ballast being put in. You can see if you look closely here, maybe some bigger rocks that were, they would just go through and basically handpick those out. So, and here's the finish line, 10 miles. I said about 12,000 cubic meters. So if you have a rail project, you know, like I said, we sometimes can use fouled ballast as the infill for the material. So, you know, we would work with you to determine if that's feasible. Here's one we did up. This was McKenna. This was a really very, very, very poor subgrade soils. I like to show this one because, you know, you can see here a complete degradation of the ballast, all the fines pumped up, and they basically started to lose the ballast into the subgrade. This is just like that British rail project. You know, you're looking at 5 meters of peat. In Canada, it's called muskeg. You know, basically it's a peat bog. This one was about 5 miles that we had to repair. This is way up in northern Canada, so there's not a very good access to get up there. So it's very hard to get up there. So we've done a lot of work with the Canadian Rail, Canadian National, Canadian Pacific Rail, So they brought us in to develop a cross section for them. Once again, you can see all the pumping of that ballast. And when the trains would go over, I got a video here. You can see how that track actually depresses and come back, and the squishing and a pumping of that ballast. So take a look at the thing. So that's the kind of you can imagine all that is every time that train went over that, we were able to get that close to the track. I mean, as you can imagine, they don't want anybody near to take a video that close to the track, but to document how bad it was actually moving, they let us get really close, and those sleepers were moving, sometimes up to 6 inches, 6 to 7 or 8 inches every time that went over, and they were extremely worried about basically the train coming off the tracks or derailment. So this was really a rush project for them. Since the subgrade was so poor, we use these, like I said, these enhanced woven geotextiles. It really does allow drainage. Something that a lot of engineers aren't aware of is that, a lot of geotextiles on these low subgrade strengths, you got to overlap them. Overlapping is pretty consistent for low subgrade soils. Usually there's a guide. There's a European guide. Here in America, we use the ASHTO, which is the highway method. It's pretty consistent all over the world too, but if you have subgrade CBRs about 1%, this would require a 1 meter overlap. So if anyone's ever been out in the field and you're trying to install a geotextile, if it's windy, it's almost like a kite. So it's very hard to not only to get that geotextile and that overlap consistent, but it's really hard to actually install it when it's windy. So the geotextile manufacturers offer factory seaming. So if you have a CBR, usually less than 1, it is recommended to factory seam them. But on other projects too, you should be aware that this is becoming pretty common now. So they factory seam these in the factory, so there's no overlap here. The cost to seam it in the factory is pretty insignificant, and you'll definitely save that in the installation time. So if you have any information about that, please reach out. I've installed hundreds and hundreds of miles of track with this factory seaming. So it really is a something good to look at. And it doesn't have to be a track job; it can be a road job or any type of job. But and once again, these are enhanced woven geotextiles, high strength, 70 kilonewtons per meter and up, and they allow a ton of drainage, but it keeps all the fines and the silts underneath. So very, very, very good geotextile. Here you can just see a couple of pictures I took. I'm just filling in that ballast rock. Like I said, this was way up in northern Canada. So, and typically here you can see the track being excavated, the geo going down with that geotextile coming up the side. This was filled in with basically an upgraded aggregate because they wanted to get some really good drainage out the sides of the track layer. Once again, just filled to the top. They did have a compactor on this, but once again, the vibration was really low. And here you can just see the finished track going into service. Like I said, this is about 5 miles on that northern route. So we also do a lot of high stress areas, grade crossings, diamonds, frogs, turnouts, a couple of really interesting applications for rail. This is a typical crossing. This is actually a project that we did in the States for one of the big Class 1 railroads here. This was a existing crossing. It had a lot of maintenance. It was basically a standard concrete panels and wood ties. It's located next to a big concrete plant. So the heavy trucks were coming to a stop and accelerating and really damaging that crossing as they're going over the top of it. So, the system failed, that whole concrete panel and the ties failed due to the excessive braking and acceleration things that were going on over it. So what they did is they tried to relate together, actually tack welded to each other to try to get this to not to failure so much. That didn't work. So they came to us and we put in a standard crossing because we want to go about 8 meters outside of the crossing. So really you dissipate that stress as you're coming on, and the other side when you're going off it. So we want to dissipate that stress before it gets to the crossing. This one was pretty interesting. This was the first installation of a composite grade crossing. So basically, this is recycled plastic, with the steel rail. So here you can see the geo was used underneath the crossing too, and you can see the enhanced geotextile again, and that geoweb being expanded about 8 meters to the other side. And here you can see the first train running through the crossing even before the geo, and it was filled with aggregate. So you can see here underneath the crossing, you can see the geocell here, and this one had 12-inch ballast, and you can see the great composite grade crossing. So a plastic grade crossing. We do a lot of crossings at night. Geocells are really very quick to install. Most of these crossings might be 1,000, 2,000 square feet. So a lot of times, our Saturday night when the train volume is down, traffic is down, they'll go in, they cut the tie or cut the rail, and remove the ties, excavate out what they have on there, and once again, we're going to stockpile that material and use it to put right back into the crossing. Usually these are completed in about 4 to 6 hours. So the good thing about it, a lot of times they're conducted by the rail staff itself. They don't have to bring in contractors, so they can really coordinate the traffic and coordinate their own crews to do the work. Like I said, usually Saturday nights, 4 to 6 hours, compared to like an asphalt crossing or some other ones where the plant has to be open. But I mean, here you can see once again, standard enhanced woven geotextile. This was a 6-inch, 150 millimeter geocell, and we're reusing that salvaged ballast that was removed, and we put right back in. This one actually was on and took these pictures. We started this about 11 o'clock, and they got done putting the rail back in about 4:30 in the morning. So, and this was the first one that crew did. So, really not experienced at all with this track staff, and they did it in around 5 hours. So, pretty successful installation. Here you can just see the ties and the rail being installed. So, like I said, this is about less than 5 hours. So, we also do a lot of interesting applications. We do a lot of bridge abutments. High stress areas when you're coming off a concrete bridge, and you're dissipating that stress onto the compacted area here. Over time, especially when it's a new bridge, depending on the amount of excavation here, you're going to get consolidation settlement. That's just going to happen. No contractor could compact it enough where, just the weight of the soil and the trains and the rail and the ties above it, are going to have some consolidation settlement. But we've been using against bridge abutments for over almost 30 years now. We've done a lot of work with Australian rail. We've done South America, here in the States, not as much in Europe yet, but and in the UK. But here you can see this is a standard abutment. This one was about 15 feet high. So on this one, we used 2 sections of web, so about 5 meters in length. There is an enhanced woven geotextile under that. And just like the other ones, we want to expand that about 30 feet from the bridge. So here you can see the rail, we stopped the rail about 35 feet. So here's the length, and that basically dissipates that stress, going onto the bridge and coming off the bridge. So you're not going to get any of that. I guess we call it the bump at the end of the bridge. You go over the bridge and you're going to have that little bump. There's a rail expert here over in Canada called Mario Rule. He really's done a lot of research on bump at the end of the bridge and why it occurs. But the real thing that geocells can help here is that since we've reduced that stress so much, reaching a subgrade, we really can control the amount of consolidation settlement. So if it's unreinforced, you're going to get that settlement no matter, just because of the stress reaching the subgrade. So over time, you're definitely going to have some consolidation settlement. With the geocell, we can't eliminate that consolidation settlement, but we can decrease it significantly. So since we reduce the stress, you're going to reduce that bump at the end of the bridge. Sometimes when we have very deep bridge abutments, I always say about maybe 8 meters, give or take, about 25 feet. A lot of times then we'll put 2 layers of geoab here at the bridge itself, and then we transition to 1 layer. So this is usually 2 panels in length. So this first area will be double wide panels and 2 panels in depth, and then transition to just 1 panel. So like I said, we would work with you, provide full evaluation, so you can see what type of stress reduction that you get at the abutment. Here's just another project. We do a lot of culvert crossings. Of course, when you have these crossings, these bridges, culverts, that you're going to have a significant amount of poor soils, usually wet, poor soils. So we use the GeoWeb here to. Oh, this one is interesting because we actually used a fabric, and we also used. I'll show you the picture. So here we actually used a enhanced woven geotextile underneath the subgrade. And we actually used a grid. So we used a triaxial geogrid underneath. The rail wanted to ensure that there was absolutely zero settlement. So they wanted to add this geogrid in here too. So you can see the textile, the geogrid, and the geosalt being put down. This was 200 millimeters in depth, filled with the crushed rock. Once again, we limited the fines here, so there would be no issues with drainage on this project. So in this one, compared to the engineer we worked with on this project, we were able to reduce the thickness of that base by over 50%. So this base with the GeoWeb was about 300 millimeters. Without the GeoWeb and just a standard geotextile, they're going to require double that. So a significant reduction, and the downtime also of rerouting that creek. So now here you can just see the finished project. We also do a lot of stations, subject to the stresses, stopping and starting of the trains. Here you can see this is actually a drainage geocomposite that was put down before geo filled in. Once you go with an aggregate rock, little aggregate being dumped and spread out with a bobcat. So we do a lot of stations, a lot of experience with that. Also scales. Scales, if you are using rail scales, they want to see almost zero deflection. A lot of the scale manufacturers will include the geocells right in with their designs. But if you got a sensitive scale or any kind of scale, you might want to take a look at some reinforcement underneath that scale. So as Roy had mentioned, and I mentioned too, this geocell guide was created back, it's going on 5 years now. So that is available through Network Rail. I'm sure Roy can help you out by getting a copy of that and showing to where it is online. But in addition to that, you really should take a little deeper dive. This is the method that I put together, and it looks at a bunch of different, not only strength of subgrade and shear stress, but it looks at a bunch of different conditions that you may run into a rail. So there's a lot of input parameters here. There's basically everything in the red I put in, the car weight, the diameter of the wheel, the moment of inertia, and the modulus of the rail itself. So here, depending on the pound per yard rail you're using, I'll get the inertia and the modulus, the type of sleeper that it is, whether it's concrete, plastic, steel, wood, and then all the dimensions, whether, the spacing, and the length of the tie, some GeoWeb information, the effective diameter. So this is a 30V. I'd mentioned it comes in 3. I think I lost it for a second there. But then some geocell parameters, and also we entered a factor of safety, and then it's a subgrade CBR. So out of that, we're checking a bunch of different, not only subgrade stiffness and what we look at, but we're also looking at the flexural stress in the rail. We want to make sure that doesn't exceed the permissible stress. We're also looking at the seat load to make sure that the seat load is not overstressed. And we're also looking at the pressure on the valves. So what is the pressure on the valves, from the train going across it? A good rule of thumb is we want to keep that valves pressure below about 85 psi. Sorry if I have it in metric, but anywhere from 65 to 85 psi. So you don't want to overstress that valve. So we do a lot of designs, and I know a lot of projects you might not have the money or the time to do like a full-scale geotechnical report or to do some DCP tests. But this is a really nice chart. I've given out thousands of these over the years. If you want one, we can get some to you. They're a laminated chart. What you can do is by basically a field ID, you can go out in the field. Say if you're walking across it and you sink about 25 millimeters, so about an inch, we can correlate that to a subgrade CBR and a shear strength. Also, if you can do hand penetrometer readings, we can basically correlate that to a CBR. So if we're interested, and you can use these on any type of project, whether it's using or not using geocells, this is a really good something to have in your toolbox if you're on a project. So in summary, we can add these to any type of rail project. It really is a flexible design. The variable infill we can use for track beds, it can be coarse sand. We can use recycled ballast. We can use clean ballast, but, very, very flexible on what can be put into it. By decreasing that stress on the subgrade, you're really going to control the differential settlement, almost eliminate basically differential settlement. But also, you're going to really control that consolidation settlement. You are going to for sure decrease your subballast thickness if you're on poor subgrades. And through that research and testing with the smart rocks, you're almost eliminating any type of ballast rotation and movement. So that's going to really have a direct correlation to the maintenance costs and the maintenance time. So, and please require a full evaluation for each of your projects based on site-specific characteristics. We provide them for free. Don't use any standard tables and graphs because each site is going to be different. So highly recommend, no matter if it's a 20-meter section of track or 100 miles of track, we actually provide the same service. So please make sure that you get that from the manufacturer. So just a couple slides on slope retention and walls. Once again, it's very flexible. We do a lot of slopes along track, aggregate, vegetated or concrete. Here's just a typical slope project. This was about 20,000 square meters on a couple sides of the track. This owner here wanted no, animals to get on the track. This area had a lot of deer, a lot of elk, things like that. So they had actually went with an aggregate solution. All of our applications, you're typically going to have some type of anchorage. So you're going to we'll do an evaluation to make sure that these geocells don't slide down from the crest of the slope. You can see just always fill it from the top down. You can just see filling under the bridge abutment here. Like I said, this was about 20,000 square meters, a project. And here you can see, took this picture about 2 or 3 years after. So it's, due to that confinement, it really does prevent any type of attrition in the rock moving down the slope. So we've done slopes up to 70 degrees. Most of them are vegetated, but it is a very flexible solution for you. This one here, this was the track over in Poland we did. Interesting one here, we had actually a wall below it. But here they wanted a vegetated surface because it was going through some residential areas. So they wanted to look like a rock. So they wanted something that is vegetated. Here you can see once again filling from the top down. And once again here we designed a reinforced wall structure below it. And then to get that slope angle a little bit less. And just a note, when you're doing a geocell solution against this is a track here. This is the main track in Montreal coming, their passenger track. Any kind of surface protection, Roy's an expert on that. A lot of times you're putting on an erosion control blanket or a turf reinforcement mat. A lot of tracks we're seeing is hydro seeding. So like I said, work with Roy. He can help you with erosion control blankets, turf reinforcement mats, and this is what the system is going to look like once fully vegetated. So very flexible solution. We can help you out with that also. Touch a little bit on some walls. We can do gravity walls, typically up to about 3 meters. That really depends on the surcharge load on top. These don't require any type of geogrid reinforcement, so very easy to construct, very quick to construct. Here you can see the geob is plastic, so you can cut around any type of barrier that may be there. Here you can see this is reinforced walls, so we're going to have a uniaxial geogrid installed here. So, and we'll size the geogrid for you, give you the strength that's needed through a program I'll talk about in a second. But once again, it's very flexible. Just dissipating this one, we use the geob under the rail too to dissipate the stress from that small little bridge abutment here. This was a high-speed rail, but also they wanted additional stress reduction. So we actually added a geob wall on the outside of it here, and the limited easement way too. So here's a project. This is what it looks like. This is a vegetated wall for a track we did not too far from where I'm in Green Bay, Wisconsin. This was constructed in the fall. So they basically hydro seeded this area. In the following summer, I went back, and this is what it looks like after full vegetation. So basically, most of our walls that we're doing, we do a lot of walls in the UK. They can be vegetated or they can be aggregate. I do have a free program if you do any wall designs. It's called GeoWeb MSE. You can easily design and reinforce gravity walls or even reinforced slopes with the software. If you're interested in that, let me know or let Roy know, and I can get you a copy of that software. And just on a final note, we do have BBA certification for GeoWeb in the UK. So if you need any type of BBA requirements, please reach out to Roy. We can get you a copy of that certificate. So with that, I know I tried to cover a lot in 50 minutes or so, but I really appreciate everybody taking the time, this late in the day to listen to us talk about GeoWeb and geocells. So with that, I guess if there's any questions, we can address them now, or like I said, here's my phone number and my contact information. If you have any questions that come up you're not thinking about now, reach out to me and I'd be more than happy to answer them. So with that, Roy, I'll turn it back over.
Yeah, thanks for that, Brian. I'm Les Fox, by the way, so I'm the chair for the Cheshire and North Wales section PWI here in Crewe, Cheshire. Yes, thanks for that. That's an excellent talk and really interesting. And it's particularly interesting for me to see how things are done in the USA. It doesn't look like it's too different to how we do things here in terms of track bed reinforcement and slopes and retaining walls. So yeah, we've got an opportunity now for anybody in the audience who would like to ask a question. So you can either unmute your microphone and ask Brian your question, or pop something in the chat and I'll read it out. I think it might be. Oh, we have actually got some questions, I think. Oh yeah, so this first comment here, I should have mentioned at the beginning, these presentations are recorded by the PWI, and unless there's any objections, they usually appear on the PWI channel on YouTube in about a week's time, should be there. So if you've got any colleagues who you think will be interested in this presentation, if you let them know, have a look at the PWI channel on YouTube. So that's that one. And a question from Alex Tomlinson here. What are the reasons for selecting coarse sand or aggregate as the infill material, and how does their performance differ? Which was exactly the same question that I was going to ask, by the way.
The performance is extremely similar. That first project I showed that we did with Network Rail in the development of that design guide, we actually tested it at TU Klostau in Germany. It was basically in addition to multiple tests that we've done around the world on GeoWeb, but Network Rail was curious to see the difference. So we put under, basically cyclical load, and the performance almost is exactly the same. It doesn't really matter on the friction angle, so the performance is really similar. The biggest thing that it comes down to is availability and cost. I would say 60+% of the track that we do is going to be aggregate and 40% sand. What we're seeing now is, especially depending on where you are, we do a lot of port intermodal yards. I think the first screen on here was a port actually in the UK that we do, but most of the port and intermodal work that we're doing now is sand infill, because aggregates are so expensive, in some of those areas that it's all sand infill. So sand is becoming probably almost as popular as aggregates now. So the biggest thing, if you're using sands and recycled materials, you want to keep that fines content at anything but below about a 200 sieve to about 15%. So that's a rule of thumb for when you're using sands and not aggregates. So another one popped up too about the steepest gradient a geocell will cope with. Yeah, I mean, normally up to about 1-to-1, not a problem with aggregate or topsoil or even concrete. We do a lot of concrete slopes too along the side of rail. Once you get over 45 degrees, aggregates, basically just want to roll down the slope even with the confinement. We've done slopes up to 70 degrees. Those are a mixture of a cohesive type soil and a topsoil that you're placing into the cells. And then a lot of times we'll wrap a core fabric around the geocell just to keep the topsoil from basically falling out of it. But Yeah, we can do pretty steep slopes. The big thing there is make sure you get a site-specific evaluation that has calculations with the anchorage in it, because you don't want the thing to slide down the slope. So, you know, what is it, a 1.5 to 1? So that's about 33 degrees. So yeah, that's pretty common for us. That picture that I showed you back a couple of slides ago for the those slopes both were 1.5 to 1 slopes. The one for Poland, the Poland rail, and then the one in the US with the aggregate, those were both 1.5 to 1 slopes. So 30 degrees. I hope those answered the questions. Like I said, my email address is here. If anything comes in, I don't know, I can share this presentation in PDF format if you're interested. If that's allowed by PWI, I can also share that. If that's allowed by PWI.
Yeah, I think if you can share a PDF version, Brian, I can pass it on to the PWI as well.
Okay.
Yeah, that'd be much appreciated. I was just going to ask on that first question where we're talking about aggregate fills to the geocells. In the UK, we do use sand blankets quite often where we've got very soft clays, you know, to filter the fines, stop it coming up and contaminating the ballast. So I guess in those situations where you need to increase the track bed stiffness and provide that filtering type sand blanket, the obvious choice to fill the geocell will be with the blanketing sand. Is that?
Mm-hmm. Yeah, that's what
so
you use
you're
on
actually
a lot of
performing two functions in one, essentially.
Yep. And those network rail slides I showed on a couple of the projects, you know, they got rid of the filter by using those enhanced woven geotextiles. Those were 70, I think they were 70 kilonewton enhanced wovens. I mean, the good thing about those geotextiles is they're inexpensive, but they provide a significant amount of strength. So 70 kilonewtons per meter is, you know, way more than any type of geogrid is going to provide. But so they provide the strength, but they also provide, you know, separation, and they provide filtration and drainage, so the water can flow freely, you know, up and down. So when we go across really areas that are wet, you're going to completely eliminate any type of maybe blinding of the sand layer, so the pore pressure doesn't build up. So it really eliminates the concern about global failure of that cross section. So those fabrics are unique products. We don't make them, but I love them. So.
Right.
And Roy can help on that if you have any questions on the types.
Yeah, sure. Do we have any more questions?
I'll share this as a PDF list to you.
Okay, right. Thank you, Brian. Yeah. If we don't have any more questions, then I would like to say on behalf of the Cheshire and North Wales section of the PWI, a very big thank you to Brian and Roy for putting on this presentation for us. It was really interesting, and it's something a bit different as well, having a presentation from over in the United States. So I was a bit worried at the beginning when Roy told me you were over in the States. I thought, oh, are we keeping you up at some earthly hour in the morning? But then I realised I think it's around about midday there, isn't it, Brian, rather than midnight? So.
Yeah, I you know, when I do presentations in Australia, sometimes it's 2 in the morning, so it's okay.
All right.
Yes, it's noon here. It's almost noon, so that's fine.
Oh, great. Okay. Right. So yeah, just to wrap up then, if we can all give Roy and Brian a round of applause, you can either unmute your microphone and give a clap, or use a virtual clap using the yeah. So yeah, so if you click your react button there at the top, you should be able to do a virtual clap.
Well, thank you for attending. We appreciate the time.
Yeah, it's much appreciated, Brian, the time you spent doing this presentation. Thank you very much.
All right, cheers.
Okay, and on that note, we will conclude the June meeting. So thanks for attending, everybody.